Okay, let's get started. So, welcome everyone. So, last time about information and rate distortion, and the first problem in the quiz is just like a straightforward application of the formulae we saw in class. So, the first question was you have been given some joint distribution table, and you are asked to compute the joint entropy and mutual information. So just go over this. It's straightforward calculation, like nothing tricky, just so that you start feeling comfortable with these constructs. And then second question was, now basically you had a uniformly distributed source on a discrete alphabet 0, 1, 2. And then we saw in class the rate distortion function, right? So the distortion we are working under is mean square error. And then you were asked is RD of RD equals to 0, right? And this you could have, you don't really need RD, right? D equals to 0 is just calculation of entropy, so straightforward. And then the second question was, what is RD equals to 1? And again, actually you didn't need any calculation for this part, because if you take mean square error distortion of 1, you could actually always transmit symbol 1. And for any given symbol, then your mean square error or just square error between that symbol and the reconstruction is always bounded by 1. Right? So if you always transmit symbol 1, you are good. And that basically means you don't really need to send anything, right? Like the reconstructor can just always recover 1. And that will basically lead to a distortion of 1. And hence your rate is 0. So this is just so that you guys again understand what's really happening. Like you don't have to always do the complicated maths. Like this is just so that you understand the concept. Okay. And fine, I think, yeah, so this was the last question, where now we were working with Bernoulli half source, and we had Hamming distortion, which we saw in class, right? So Hamming distortion is just distortion is 1 if symbols don't match, and it's 0 if symbols match. And for this source we saw, so Tsachy worked this out in class, that your rate distortion function turns out to be 1 minus the entropy at probability distortion D. And then we asked which of the following is correct, right? And so again, it's a quite straightforward thing. It's just so that you understand what the rate distortion statement says. And so what it says is that, like, so basically there exists a scheme which, when working on large block sizes, which achieves distortion D, and your rate always has to be greater than this RD, right? You can't compress more than this RD. And so first one is wrong. You can't actually get rate more than this. Second one is correct. You can get rate greater than this. And actually what Tsachy talked about is, we didn't show the proof, but this is a much stronger statement. This is exactly analogous to the entropy case, right? Where you can actually get arbitrary close to. If you allow me to take larger and larger block sizes, larger and larger symbols, I can get arbitrary close to this. So the third option was also correct. And finally, what's really important is this large block sizes, right? So this allowed us to do this asymptotic analysis. So if you recall from last lecture, Tsachy, for example, even for Gaussians, where he had the sphere packing argument, like it was contingent on the fact that you're working on really large dimension. That's when you will have sort of minimal overlaps, right? And so this part is really important. So again, it's very similar to entropy. Entropy, it doesn't say you can do it symbol by symbol, but there exists large enough block sizes where you can achieve that. So this is actually untrue, right? That working on single symbols, there is no guarantee that you can actually achieve this. Okay, any questions on the quiz? Cool. So let's just quickly recap what we covered, and oh, sorry, I keep clicking this, and then continue on to. So today's lecture will be building on what we learned in last class, and then learning more about transform coding, which is a new technique. So quick recap. So last time we first learned about mutual information, right? So information is y, two random variables, and let's say I have joint distribution px of y. Mutual information, okay? Right, and you calculated mutual information using this. There are various other versions of the mutual information formula, but like this is like the basic definition. Then we learned a bit about Shannon's rate distortion theory. And again, in Shannon's rate distortion theory, assume that you have x1 to xn symbols, which is some data which is generated IID. right? Then the optimal rate R of D for a given maximum distortion D. So this is like the best you can do, like the minimal rate you can get for that distortion is given by the minimal mutual information. Minimum over expected value of distortions xy less than equals to D. Okay. And just in case it was not very clear in the last lecture, your expectation is minimum over all distributions x comma y, all joint distributions x comma y, which you can also think of being factorized at px qy given x, because this term is sort of given to you, right? Like the px is given to you. You have some source which follows some probability distribution. And so what you are doing is you are allowed to come up with any constructions of y which minimizes this mutual information to give you the optimal rate distortion. And another important thing to note here was that we were working with IID data, and a distortion really was a symbol by symbol distortion. So let's say xn is a n tuple of symbols. So this we approximated it, not approximated. So we assume that I can calculate my distortion symbol by symbol. So if I have a n tuple, so this is just x1, x2, xn, and similarly y1, y2, yn, that my distortion is basically per tuple sum. So another small point to be careful about. Okay. And then we actually worked out also a Bernoulli source under Hamming distortion, but something which we are going to use in this class repeatedly to drive home some points is this Gaussian source under mean square error distortion. So again, like whenever we are talking about RD, be careful about the source distribution. Obviously that determines the like how well you can do, but also the distortion. So if it's not clear, always ask this question. If somebody comes and tells you what's the rate distortion, do ask under what distortion are we working. Or if somebody comes and asks you to design a lossy compressor, like do ask what's the right distortion to work with for that particular application, that particular source. So specifically again for Gaussian and mean square error distortion, we saw that like, okay, if x is some normal 0 comma sigma square, you have some Gaussian, so actually this shouldn't be unit. So in class, we saw the case for x normal 0 comma 1. So I'm just generalizing it to now normal 0 comma sigma square. So it's like you can work out exactly similarly, just variance scaling 1 to sigma square. And a symbol by symbol distortion was this, just mean square error. So you're gonna square the differences. We saw that the rate is given by half log sigma square by d if your d is between 0 and sigma square, and if your d is greater than sigma square, your rate is 0. Okay, so this is really important. So what this is saying in this Gaussian case, think about it, is that if you are allowed very large distortion, if you are allowed it to be larger than the variance in your symbols, right, then you don't actually need to transmit anything. Right, because whatever the mean thing you recover, so we worked out the maths earlier, like expected value of x given y in this particular case, like whatever the single symbol you are gonna recover, it's basically guaranteed to have the mean square error always less than d. It's actually always guaranteed to have the mean square error sigma square, right? That's what it means. Right, so in this particular case, if I always transmit 0, I know that my expected value of x minus 0 whole square is actually sigma square, which is always less than d, right? So I can always transmit 0. I actually don't have to send over anything, right? But if my distortion, maximum distortion which I'm allowed is less than sigma square, okay, then I have to be intelligent in selecting my code book, right? And what you can show is that when you do that optimally, again using one intuition was that sphere packing argument, like that beautiful high dimensions sphere packing argument which Tsachy gave. You can show that the minimal rate you can get is this term, half log sigma square by d. Okay. So another way to think about it is if your source have low variance, right, you can actually get away with much fewer bits. Does that make sense? So if my sigma is really low, I can get away in life with lower d. Because you are saying my symbol is very tightly bound. So if you allow me to have very large distortion, obviously I can just throw away a lot of information and just get away with a single symbol. right? So this is just another way to look at this formula, like very simple formula, another intuition which you are getting through that. Yeah, everyone with me? This is really important, and we'll see sort of trivial extensions to this, but which actually results in, I would say, not so trivial practical implications. Good. Yeah. So just another smart thing, just notation wise, sometimes we write this as this, so Tsachy also mentioned this, but just as a revision point, where you can write RD actually as Rx comma D, just to highlight that what's really your source, right? And so for Gaussian, we might write it as R subscript of G, just to say Gaussian and just directly say the variance, which just means mean 0, and distortion D. And there's this another notation which you can write it as. So you can see that if D is greater than sigma square, then your sigma square by D will be less than 1. And this whole term would be negative, right? So another way to think about this plus is just max of 0 comma x. So this is how we define x plus. So this is just like another way to write these are equivalent, right? So if sigma square is greater than D, this quantity is positive, and you can just write half log sigma square by D. If sigma square is less than D, this quantity is negative, and we are not taking negative value, we'll just clip it to 0. So just like a very simple mathematical notation. And finally, this is what I wanted to show you last class, but we also saw it the class before. So this is the performance for, again, like the Gaussian source, normal 0 comma sigma square. On the x-axis, I have rate. On the y-axis, I have the mean square distortion. The red curve is, so since my x-axis are instead of RD, I'm just plotting. So if my RD is half log sigma square by D, then my D of R is just 2 raised to minus 2R. So actually this is for sigma equals to 1. So 1 second. So my D of R would be 2 raised to minus 2R by sigma square, right? Yeah. Okay. So here I'm just plotting it for sigma 1. The red curve is the theoretical best which you can do. And the blue points which you see here is with respect to, so GL is generalized Lloyd, but you can think of K means with K equals to 2, okay? And this is really important, right? So what these plots says is this red curve which you see here, correct? So this red curve is the theoretical best you can do. Like come up with any scheme in the world, take as large block sizes as you want, right? Do your best. You might have to do a lot of effort. We saw in vector quantization, it's not trivial as you keep increasing the block sizes, right? So this red curve is what you would have obtained. And with just doing k-means with k equals to 2 and taking those vector quantizers, so just working with the two-dimensional vectors for our code book, we can already get a performance which maybe looks like this, or these blue points. So you can see you can, depending on the application, it's maybe okay to just work with this practical scheme, right? Like the overhead which you are getting, you might have to pay a lot of cost in terms of complexity. Okay? So even though this scheme exists, it's just to show you comparative performance. Yeah, and sorry, this is my bad. This is wrong, obviously. This should be this, right? Because sigma square by D is 2 raised to 2R. Sorry. Okay. I want to reiterate this point. It's going to come again and again. So one thumb rule so far, which we saw about lossy compression Gaussian case, is that basically for a given distortion, you would like to allocate more bits to components with higher variance. Right? If your variance is really low, you can get away with giving sort of lower number of bits to it. Correct? This is just like what we discussed here. This is like one way to think about like what we saw, one intuitive takeaway. And does it make sense to everyone, like even just intuitively, right? Like if you have higher variance, you need more bits, sort of more codebook points to cover so that you have some constant distortion. Whereas if you have lower variance, some data is spread less, you can get away with fewer points for same distortion.
I think you meant distortion level.
Yeah, distortion level, sorry. Thank you. This should be level. Thank you. Yeah. Okay, so far everyone with me? Okay, so then today we'll learn a bit more about this water filling intuition for correlated Gaussian sources. So far we have been working with these IID sources. We are not going to look at a general correlated source just yet, but this is going to give you some intuition on, again, what you can do. And then we'll use this intuition to learn, to motivate, I would say, transform coding, which is just sort of, I would say, it's omnipresent in all lossy compression techniques in some way or the other. Okay, so let's get started. So again, your lossy compression framework, which we have been seeing, right, is this. So you have some source symbols x1 to xk. You encode it into some n codebook vectors. And so your rate is log n by k. We have seen this, right, bits per symbol. You get some bits. You transmit this bits to the decoder, and that recover these hat symbols, right? And so the two terms for lossy compression really is the rate, because you need log n bits, and you use them to transmit k symbols. So it's log n by k bits per source component. And then your distortion between these two, what you recovered and what was supposed to be encoded. And as we saw, like, we are working with memory-less sources or IID sources, so we can just easily break it down into individual components. So last time, the Shannon-Sadi theorem which we saw, it assumed that your x1 to x2 is IID data generated, right? And in that case, we saw that optimal rate RD is given by this. If you, again, like, I want to reiterate, it's really beautiful that we could come up with something closed form in this case. This is like optimize over all possible schemes, right, in the world, which you could have done for this particular source. And that gives you, like, this is a very nice formulation, mutual information, right? And we got this. But in reality, your data is not IID, right? In reality, your data is correlated. So what can you do here? And actually, you can show that you can generalize the Shannon. So, like, next few statements are going to be without proofs. And if you're interested in the proof, please take EE274, which goes into much more depth about all of these things. But now let's say you have some source block xn. So again, this is what we have been looking at, right? Just x1 to xn symbols and your reconstruction x hat n. Then you can show that your rate for xnd is actually given by this, again, formula. And here the mutual information is between symbols xn and x hat n. Okay? And now you have not assumed anything about xn's. You haven't assumed that xn factorizes as IID. So, like, the probabilities are going to be just multiples. It can be anything, right? And remember, like, this whole minimization was under the joint distribution, right? So here, this minimization would be under joint distribution of pxn, px hat n. And it wasn't obvious that the Shannon theorem will generalize for this particular case, but it does. And one way to think about this is like, just your Rx comma D was the analog for entropy in the lossless case for X. Rxn comma D, you can think of it as an analog for the entropy of the n tuple. Okay, so this is just like generalization going beyond IID. And actually there is another level of extension. So now if you assume that you have a stationary stochastic process, which I'm gonna denote by this boldface X. So you have x1, x2, x3. Shubham talked about stationary stochastic process in the, I think in lecture 8, right? In that case, what you can show that is there is a quantity rate x comma d, where x is now your stochastic process. And this can be calculated by taking the limit n tends to infinity of this tuple xn. So this Rx n comma d is just the rate distortion for the tuple xn. Okay. And again, like if we have to bring analogs, this Rx comma D is the analog for the entropy rate of the n tuple, right? So like we talked about entropy rate, and we took that limit n tends to infinity there, right? Similarly, we are basically doing the exact same parallels like what we did in lossy compression, and we show that like similar generalizations exist for Shannon-Hardy theorem as well. And what you can show is that this limit exists basically for stationary sources. Again, I'm being hand wavy, but that's intentional. If you are really interested into the maths of this, please take EE274, or we can point you to specific resources like how you can show these things. But the main takeaway is really this, which is the best you can do for stationary processes, okay, in the limit of encoding arbitrary many symbols in a block. So we are not worried about the complexity at all, is basically this term, Rx comma D, this stationary process term. Okay, so haven't really done anything different so far. Just what we have shown is that we could have used whatever we have done with Shannon's theorem for also correlated sources. But now this term might be hard to compute in practice, like we saw, like even in entropy, other than simpler cases, we didn't really do much. But I think it is interesting to look at one specific example of like how you can use this theorem on, like it has a lot of intuition. So first of all, I'll pause for a second. Any questions? Everyone's with me. Okay. So now let's work through a very specific example. Assume you have a Gaussian source, and we are going to work with block sizes of 2. So we are going to always remember this picture, I think, when you are thinking of lossy. So you input k symbols in a block into the encoder. And so here we are going to work with k equals to 2. Oh, sorry, I think I went ahead of myself. Yeah. Okay. So let's say your x1 is a normal sigma 1, 0, sigma 1 square, x2 is normal 0, sigma 2 square, and let's assume they are independent still for now. Okay. And then the way we have been looking at blocks, x2 is just x1, x2, like is just a 2-dimensional vector, right? So what you're going to do is like at each sort of like one way to think about is I'm going to sample x1 with normal 0 comma sigma 1 square. I'm going to take a sample from normal 0 comma sigma 2 square, combine them, I'm going to lossily transmit it. Then I'm going to repeat this process, and I'm going to keep doing this. Okay. And this is just the notation. So a notation now for this x2, Rx2 comma D is just, I'm going to call it G, and then I'm just going to replace it with sigma 1 square, sigma 2 square, because that's what matters. This is just like generalization of our single dimensional notation, comma D. Okay. So in this case, what you can actually show is your rate distortion for this, if you were doing in blocks, independent Gaussians. You can show that it turns out to be minimum of half of alg sigma 1 square comma D1 plus alg sigma 1 square, oh sorry, this should be sigma 2 square. Let me just fix it. Should be sigma 2 square, alg sigma 2 square comma D2, and just half of it, such that your D1 plus D2 average is less than D. So essentially what you can show, we are not going to work this out, but this is like, I would say it's almost straightforward. We can talk about it, but okay, what this really means is that I can independently lossily compress my source 1, give it a distortion D1. I can independently compress my source 2, give it at a distortion D2, but now since I'm doing it and doing them together, my average distortion should be less than equals to D. So in some sense, what it's allowing me to do is break my distortion D, and it's allowing me to give a distortion D1 to source component 1 and a distortion D2 to source component 2, such that on average, my distortion is still less than D. And then it's basically allowing independently optimize over each channel. Okay, so the question really is like, what is D1, D2? We'll figure that out in a second, like what's the ideal split I should give. But this you can show from like almost straightforward. Like if you just, for example, expand the mutual information out. So in this particular case, you can just work out the mutual information. You know how we worked it out for a 1D case. Similarly, you can work it out for the 2D case. And you get this. You get this nice looking formula. And I think this mistake, by the way, might continue a couple more slides. So just like bear with me. If you're getting confused, let me know. I'll fix it. Okay. And so this is just rewriting our formula from previous slide. And so we know what my RG sigma 1 square comma D1 is, right? So that's just Gaussian with variance sigma and given distortion D1. So again, I think this is, and so here it's just straightforward substitution of what we saw in last class. Okay. So this now becomes our RD problem, right? Like which we need to solve. So what we really need to solve. So rate for my this source given distortion D is basically an optimization problem such that my minimum over D1 plus D2 by 2 is less than equals to D, and this is my objective function. And again, so it's very simple. Like what we are saying is, find me the right split of distortions between source component 1, source component 2, such that if I independently encode them together, I get like the minimal rate. So what's really this optimal split? So you can, like if you have taken a convex optimization class, this is actually quite a straightforward minimization problem to solve. You just solve it using KKT conditions. But let's just look into the answer for intuitions. Like if you haven't taken, it's okay. We can discuss how exactly you solve this problem. It's not the point of this class, but trust me, it's not hard to solve. It's like very standard techniques. Okay. So let's talk about it. Okay. So without loss of generality, so WLOG is just without loss of generality, let us assume my sigma 1 is less than sigma 2, like the source I'm encoding. And then this is, I need to figure out how much distortion should I give to the first source, which has sigma 1, and the second source, which has sigma 2. Okay, so my of distortion which I'm giving, the amount of distortion which I'm giving to the first component to be greater than sigma 1 square. A few heads going in various directions, but I would like to see maybe a few more. Is the question clear to everyone, first of all? What we are trying to do? Okay, would anyone like to answer? Yeah.
Oh, if it's greater than sigma 1 squared, well, if it's equal to that term is going to be 0,
Mm-hmm.
it's greater than this will be 0, so then all you're doing is basically taking away distortion from E2, and so E2 gets smaller, and the right term gets larger, so
Okay. Yeah, so that's basically the answer. So I'm gonna just repeat the answer which student gave is that, oh, if my D1 is greater than sigma 1 square, then anyways this rate term is going to be 0. Any more component of distortion which I give to the source 1, it's basically taking that distortion away from the second one because my total distortion needs to be constant. And that's wasted anyways. It's not reducing my objective term at all. And so it doesn't make sense to give distortion 1 ever greater than sigma 1 square. Again, I see maybe just let me write it down. Remember this thing, what it means, right? So this was the rate term for a single Gaussian, and this was just half log sigma square by d, if my d was between 0 to sigma square. But it was 0 if my d was greater than sigma square, right? So if my distortion which I'm allowing is greater than the variance, after a point, like, it doesn't matter if I distortion, I can anyways get away with 0 rate. If you now allow me that, okay, like you can double the distortion. Well, I can already get zero rate with half that distortion. Why should I ever like take away that distortion from the other component and give it to this one, right? So just very intuitively, we are talking about this objective function. So the answer here is no, you shouldn't, right? Okay, and then what is the R of D1? What I mean by R of D1 is this term. So this, you can think of it as number of bits which I'm giving to the first component, which I'm giving to the component, right? And so if my, again, D1 is greater than sigma 1 square, how many bits am I giving to the component 1? Anyone?